There are no weight classes in game development. There are no divisions that are going to keep the fights fair. So you and your team and your game may be competing against games from teams of vastly different sizes with vastly different budgets. And there are some AI, UI, and performance tricks that you can do to stand up to the Goliaths and stand out. So maybe this is you, or maybe this is you, Ubisoft. But anyway, maybe you're on a small team, so maybe this is you. So I'm going to talk to you today about Race for the Galaxy, because that's the game that I've most recently worked on. And this game has a neural network in production, and it's been released to the players. So I'm going to talk about some of these AI, UI, and performance tricks that are going to apply across a lot of different kinds of games, but not all of them, and I'll talk about which ones and why. So in Race, our neural network creates its own training data, and we run this neural network, AI, on a separate thread to keep high performance. And we conduct the flow of events from the AI through a series of locking attention tokens. So a few smart innovations like this are going to be able to help you stand out in the ring. So I'll talk through what these are. But first, I want to tell you a little bit about why we made Race for the Galaxy. So this is us. We're a really small team, just 4 people. That makes us a featherweight in this scenario. So we're going to be up against middleweights. We're going to be up against heavyweights. What can we do? So our games are sold on the same shelves next to these bigger games. And many consumers will know which games are coming out of the AAA titles, but sometimes your game is really just up against these, next to it on Steam, for example. And people don't know that this game was made with millions of dollars and this game was made by a few friends. So how can you compete? And not only that, your games may be, especially if you're a featherweight, competing against thousands of other featherweights. So I'm sure you've all heard the statistics, 40% of all games that have ever been released were launched in Steam in 2016. So it's very easy to get lost in the shuffle. But something you can do to stand out is choose a niche. And you can choose a niche because you're small, so you can leverage your size. Your budget may be small, your time investment is short, potentially, which means that you don't have to necessarily hit a mainstream market. So for us, we initially chose VR. So we had been experimenting a bunch in VR. That's the team. That's basically how we work. And we had made this game called Bazaar. And it was really cool. It was a flying carpet roguelike. But the thing that really stood out was that it was really lonely. It was something that we wanted to share with our friends. So in the next game that we made it multiplayer. And this is something we wanted to do because we wanted to create lobbies to bring players together. But you can't just do that. You need to give them an activity to do. And since we all like playing board games, we made our favorite board game, Ascension, in VR. And Ascension is a deck building card game. It's pretty cool. But we had a problem. So our problem was there weren't always enough players. We had the dreaded crickets. If you make multiplayer games, you know about this. And part of the reason for that is that VR is fairly immature market. The headsets are exorbitantly expensive. You know, to have a PC that runs your VR headset, it's going to cost you a lot of money, and all of this is going to amount to friction in getting your player into the game. And so we needed an AI to compensate, a good AI, to compensate for sometimes the crickets. And in VR, that AI needs to come to life. So what it's trying to do in a strategy game like this is give responses about what the state of the game is. Is the AI pulling off a good strategy? It's going to do a victory animation. If the player is taking a long time, it might tap its foot, just to emulate what another player would do. But underneath the hood, the AI for this game was very heuristic driven. So it was basing its decisions on expert plays with human input. So for example, it would choose to purchase cards that had a high victory point value compared to their cost. And if you know the game, then some of this will make sense. But if you don't, it's basically a strategy card game. Oftentimes you have victory point value, sometimes you have a cost associated with it. So other things that it would do based on heuristics are, it would buy a heavy infantry or a mystic after buying cards from the center row. It would play all of its cards before making a purchase. even though the purchase phase isn't limited to the end of the turn. It would destroy the most expensive construct an opponent owns. It would trash militias or apprentices before trashing other cards if it's trying to cull its deck to be a lean deck. And all of these things made it pretty good. But I'll talk about how you can make it even better than a heuristic driven. So when figuring out what our next game was going to be, we wanted to double down on our strengths. So for our team, our strengths were AI, UI, and performance. So the next game that we made was Race for the Galaxy, which is another strategy card game. And this is an engine building card game set in a sci-fi universe that's really cool. The AI in this game is pretty different. So this one's not the heuristic driven AI. This one is driven by a neural network, and that makes it much, much more challenging for the players. So this neural network driven AI was actually originally published by Keldon Jones in 2009 as an open source research project. And in the last 5 years, there's been a lot of advances in neural networks for natural language processing, computer vision, autocorrect, delivering the right ad content. But before all the hype, Keldon was starting to apply these neural networks to board games. And this is based on TD Gammon, which was a project by Gerald Tesoro. So this is one of the coolest neural network-driven game AIs out there, and it's based on a game over 5,000 years old, which is backgammon. But this AI was ultimately able to challenge conventional wisdom and challenge game theory about how backgammon should be played, even though this game has been accruing expertise for 5,000 years. And it did that by coming up with unorthodox strategies and using a neural network. So if you play backgammon, this might look familiar. So conventional wisdom said that if you, on your opening play, rolled a 4-1, you would do a strategy called slotting. So you would move your white checker over here 4 slots and your 6 to the number 5. And what you're trying to do there is, as your checkers are moving counterclockwise for white and clockwise for brown, you want to put a checker here because then your opponent's going to go and they're going to roll. If they roll something that amounts to a 4, they can go here, 2, 3, 4, and bump you out. But if they don't roll something that amounts to a 4, which is a small probability, you can get a menacing defensive position here. So this was commonly held to be the best way to play. But actually, TD Gammon by Tesoro figured out that a more optimal way to play is a strategy called splitting, which is instead of moving that one checker over here, you actually move one over here. And I don't need to get into the whole strategy on why that's better. The statistics bear out on the game. It ends up winning a little bit more often. And you can see the score here. This is the AI's splitting strategy. This is the slotting strategy. And it's prediction at the turn, and then the result of whether it was better or not. And it ends up being better to do the splitting strategy. So how does this AI come up with a strategy that's different than people? It's because it has zero initial knowledge. So you guys have probably seen a couple of the talks already on reinforcement learning. This is basically what this is. So unlike a heuristic-driven system, this is teacherless. It doesn't have any information coming from a human, which is actually pretty good because human information can be very fallible. So what it uses is reinforcement learning. It's going to learn input. It's going to produce an output, receive a reward, and that reward is going to be a feedback signal from the end of the game, and the goal is to choose the best action on any given turn to optimize for that reward, or that score at the end to be higher, basically. But the score at the end is delayed because that reward is coming from whether the game won or not, and that's several turns into the game. So what do you do at the turn level at each, basically, time step as you go? You can assign a temporal, credit, or blame, and that's what the crux of the temporal difference neural network is all about, temporally successive predictions, and I'll go into a little bit more on that. But basically, Keldon had built a bunch of these different neural network AIs, and you can download them because they're open source. In fact, I did. And I did that because I was looking at my favorite board game, Race for the Galaxy, to see if there was an online client, and there was this open source project. And I started playing it a lot, and there was this feature I really wanted, which was if I was shifting my focus from the application to check my email or browse the web or something like that, I wanted a notification that another player had taken their turn, so we don't just get like in a stalemate of nobody taking their turn. So I wanted to add a sound effect for that. And Feature Creep City, I kept thinking about what else I wanted, and the number one thing I wanted was for this to be on my phone. So I got in touch with the game designer, Tom Lehman, and turns out he was local. And sometimes people ask how we get the IPs for these like crazy games like Ascension and Race for the Galaxy, and I think if you just like bombard someone with your enthusiasm for their game, then they'll trust that you're gonna be interested in the strategy space and care a lot and do a good job. He just had one request for me. He said, you should look up this guy, Keldon Jones. He did a pretty great neural network AI. And I said, okay, you got it. I'm already a big fan. So Keldon's AI is not actually just one neural network. It's bifurcated into 12 separate neural networks. And it's important when you're doing your temporal difference neural network for reinforcement learning to make these bifurcations smartly. So for us, what we're doing is we're saying, okay, we're gonna have one neural network that's gonna cover a 2-player game with XYZ expansions. And then maybe we're gonna have a different neural network that's gonna cover a 3-player game, maybe with expansions off. And there's, so on for the different permutations of numbers of players you can have, as well as different game options you can turn on and off. And the reason you wanna do those bifurcations is you're training, just like in the talk earlier, if you caught it with the racing game, you wanna train your neural network to be specialized in a particular set of parameters. That one was the vehicle classes, but this is just like the parameters for your game you're setting up. You can always partition your game or your neural network to infinity, but you don't want to. You want to be a little bit smart about it, because partitioning it is going to add a lot of complexity and it's going to add a lot of size to your game. So for us, our neural network ends up being about 1/4 of our download size, which is actually saying a lot because we're making a strategy card game and they have a lot of artwork in there. So for each of the 12 different neural networks that we have 2 different flavors each, so we end up having about 24 neural networks in our game. And the different flavors are to accommodate different functions of what we're trying to get out of them. So the first one is a function where it says, given what move would player X make in state Y, and that's just trying to figure out what is your opponent's action going to be. And the other is, given this game board, how good is it? And that we call eval board. The first one is eval roll. And on its turn, the AI is going to simulate through all of the different actions it could take and run eval board neural network on them and choose which one has the best score and choose that as the action that it's going to take. And for moving the simulation forward, the AI could be running one or more different calls to eval roll to figure out what other players are going to do in that simulation. So, sure you guys have seen this all before, but this is using a multi-layer perceptron architecture, and you've got your inputs. We've got about 150 hidden nodes, and your outputs, you've got weights along the edges that are going to be adjusted every single turn based on the reinforcement learning. And we run all of this through a sigmoid function. We end up using hyperbolic tangent to expand it out so that you're not dealing with just a linear function, because you don't know if you're looking for a linear function with your neural network. So at the end of the day, your neural network is a black box that's just trying to emulate a function that takes your inputs in and gets outputs and matches the training data. So in our case, for our inputs, we have about 800 different nodes that describe the state of the game. Those are going to be things like, well, it's 800 for a 2-player game and then 200 more per player. And those are going to be things like what cards are in your hand. Someone was asking me yesterday, how do you process the cards in your hand? It's just a Boolean for every single card in the game. So that's why it gets a lot bigger for the expansions and stuff. And is player X winning? How many goods are on the cards? It's an engine building game, so there's a concept of goods getting converted into victory points. So just basically all kinds of things that are going to describe the state of your game. And the outputs are those scores based on the functions you're looking for. So eval board, it's going to be the win probability for each player, and then we only look at the local player. We get the score for that, and we have that as the eval board, which is just basically the equity of the board. And let's see. So this is the formula that we use. I guess I don't need to go into all the details here, but basically what this formula is doing, and this is the one developed for TD Gamma, we use something really similar. What this formula is doing is it is going to be adjusting how much, calculating the weights that are used for reinforcement. And so the first number is how much you're going to change a weight from its value on the previous turn. And then alpha is a learning rate parameter. We have the difference between current and previous turn board evaluations. And the rate of decay in backpropagation. Backpropagating older estimates, I'll talk a little bit more about that. And how much changing the weight is going to affect the output. So what's cool about this kind of neural network is the outputs are context sensitive. So a move is not necessarily black or white, good or bad, like you would get with the heuristic-driven AI. So for us, in this game, there are cards with a high intrinsic victory point value. This is kind of a bad example because this actually has a dynamic victory point score, but just pretend you don't know the game. So in a lot of games, you're going to want to go for cards with high victory point value. But in this neural network, because the context-sensitive nature, you might not want to choose a card like this at the beginning of the game. So if you play a lot of strategy board games, you know that you may want to be waiting on the victory points until towards the end of the game. And in fact, getting something with a high victory point value at the beginning of the game could be a liability because you could be, hosing your economy early game, or you could be missing out on an opportunity that would be more engine building, that would give you more dividends as the play goes on. So a neural network is better at differentiating when a play like this might be good. So I guess everyone uses the cat example, but neural networks get better by adjusting their edge weights so that the computations result in inputs and outputs better matching the training data. So that training data usually comes from people. So normally you're going to say, hey, like if I'm trying to figure out if an image is a cat or not, you're going to have a human feed in a bunch of pictures and say that they're cats. But with our system, we do something a little different, and that's based on the TD gammon. So for us, where do we get our training data? Because it's a reinforcement model, this training data is auto-generated. At the end of the game, we can see, did the player win or not? If they won, we give them a score of 1. If they didn't win, we give them a score of -1. But it's not just about that. It's not just about the end of the game. On every single turn, we're training the neural network because we're making a prediction. On turn n, we're training turn n -1. So if you're on turn 3 and the game says, I think that player, or if you're on turn 2 and the game says, I think player 3 is going to win, and then you're on turn 3 and the neural network says, I think player 5 is going to win, it's going to go back to turn 2 and weight it a little bit more towards player 5. So at the end of the game, your outcome is going to affect the neural network, but on every single turn, it's going to get trained a little bit more. So we've ended up running this neural network through training for about 30,000 games. But we don't just have 30,000 results because each of those games has up to 4 players and 12 to 15 turns each. So it ends up being closer to 1 million pieces of information to train. So using a knowledge-free system frees us from the human input, which is really cool because there are 2 benefits really. 1, it's super cheap and it requires little human input, and 2, you are rid of that bias. So the neural network only knows the rule of the game going into it. So it's not going to be hampered by the dogma or the doctrine that's been conventionally accepted, and you'll see emerging strategies that propagate back from your neural network to the player community. So just like with the slotting versus the splitting play that got back propagated to the player community, we're seeing that with Race for the Galaxy. One example is when people typically play Race for the Galaxy, a lot of times they will get emotionally stuck in a strategy style. Are they playing offensively? Are they playing defensively? Are they following a particular color of good for their economy? And what you see after you play the AI a bunch is that the AI doesn't maintain this allegiance to a particular strategy and ends up being very effective, and then players take that back into their play strategies when they just play at their kitchen table and learn from that. So initially, when we start training the AI, it has no real strategy whatsoever. It's totally random in what it's doing, but pretty quickly you'll see tactics start to emerge. Tactics such as playing it safe or piggybacking. So in Race for the Galaxy, is a card game, obviously. The AI here in this case is doing piggybacking. So the AI has chosen to trade, and that might seem really dumb if you know this game at all, because it has no goods to trade. So it's basically wasting a turn, except that the AI predicted, maybe, that I'm going to settle, and when I settle, every player gets to settle, the AI can settle a windfall world, which comes with a good, which means by the time the trade phase comes up, it has a good to trade. The AI has discovered a piggybacking strategy, which is something that players have discovered as well, on its own, completely devoid of any human input. So, do we continue to train this AI on the live version? No, because we find that that is going to slow the game down. And we find that the AI has basically peaked. Neural networks like this have really good scaling behavior. So at the beginning, they're playing really badly, but as they go, they get substantial improvements in their strategies. And we find that training against humans might actually make it worse, because it usually trains against itself, and people might make it a little bit worse. So we'll have to continue training it if we introduce more expansions, but we'll probably do that offline again. So the result of all this is that your AI is going to be really difficult, which makes it really, really replayable, and your game is going to be able to stand up a little bit better against some of those heavyweights. For us, having a really difficult AI, executing it with immediate performance at 60 FPS on a phone, and UI that communicates the AI actions, and keeping our performance up, keeping our AI on a separate thread, things like that, are what helps us keep the game running really smoothly across platforms. So you might think that having the world's hardest AI is not the best decision for every player, and you're right. So people like easy AIs when they're new, but there's a really easy way to make your AI easier if it's a hard AI. And the reverse is not true. So you just add a little bit of noise to the score from your output, and that can make the AI choose the second most or the third most best decision to make at an action space. So you can tune this noise to figure out what your AI difficulty levels are going to be. A good goal is to tune it so that your medium AI wins in about 25% of cases against your hard AI. So when you're incorporating this AI, you're going to want to use UI to communicate what is going on with the AI players. And you can, in the game, communicate each event by the onesies, but your players probably won't tolerate that very well. It's really boring. And I see a lot of other board games out there who basically just give you a slider where you can speed it up, and then that just makes it incomprehensible. So if you're doing this, communicating your events through animations by the onesies, it can be very clear what's going on, but it's bad in terms of monotony. And we started this way, and we realized, what are we really trying to communicate here? We're trying to communicate high-level state changes. Like, these are things that are communicated with the UI that's been developed for thousands of years with just board games in general. Shuffling cards, drawing cards into your hand. These movements of the pieces around the play area communicate that the game state is changing. So we wanted to try to focus on that. And it's really hard, because if you've played Race for the Galaxy, you know that the player turns are simultaneous. There's a lot going on. People can be drawing cards, people can be settling worlds, they can be building developments, and as a UI person, this is kind of what it feels like to me. You're just at this crazy intersection, and there's just a lot going on. So what we did was we came up with a system of locking attention tokens to try to communicate this information. So basically, if you have an event that's really important in the game, like one of the AIs is settling a planet, we say, okay, that deserves the main attention token. Every other thing that's going to deserve the main attention token has to queue up and just wait for it. Meanwhile, there's about 10 other locking attention tokens with varying priorities on the player attention. So something like, a player just grabbing a couple of victory point chits from the pool is not that important to communicate. We put that in a sort of like inferior attention lock. And that stuff can just kind of happen in the background without losing the attention on the main events that are happening. And that's a good way to clarify with a complex game and an AI that's executing everything really fast, to slow it down, show the player what's going on. Also, if you're doing board game AI, it's really important to have fine-grained control over the clocks in your game and the timing. And this is something, again, that we have been able to do because we have a custom engine. So in communicating your AI, you want to manage the flow of information. It's not just where you're placing things on the screen, it's how fast you're moving them around the screen so that players can keep up with what's going on. And if you manage to so your performance is right and so that your UI is displaying what's going on with the AI right, users won't know why they like your game. They won't say, oh my gosh, I really like this game's performance. They just know that they do like it, and we're seeing, after we had been out for 2 months, we're seeing players who had played upwards of 6,000 games, a game being on average 10 minutes, but can be as fast as 4 minutes. So that's hundreds of hours, and this game has, if not the top selling board game out this year, paid board game, it's one of the top ones. So these are good tips. So in this talk, I've talked about the AIs we've made, how you can apply them to board games, and I want to tell you a little bit about how to choose what kind of AI you're going to apply if you're doing any kind of board games. And these AIs are going to help you compete because they're going to extend the depth and scope of your game. So I have a little checklist for you if you're considering a temporal difference neural network like we've done. So first off, is your game a board game? It doesn't have to be, but board games require complex sophistication. The rules are well defined, so these are really good candidates for this kind of neural network. Again, like people have been mentioning, stochastic games are good candidates. Anything where you have a high RNG that's going to come from dice rolling or deck shuffling, any bit of randomness is going to create space in your probability trees for the neural network to discover novel strategies and also just try a wider variety of things. If you don't have that randomness, like if you have a deterministic game like chess, you don't have that space for the neural network to really explore and find if one strategy is better than another one. Oh, and if you do have a deterministic game, you could theoretically introduce some noise, and that would give it a little bit of play space to explore. So furthermore, because of this randomness, you're going to have a really high branching ratio on possible outcomes for the RNG variables. So what that means is a deep search, like you might be using for chess or Go or something like that, is going to be computationally unfeasible, even with a supercomputer. So that's why you might go with one of these neural networks. And if you're using a temporal difference neural network because you're making a non-deterministic game, you want to be using a game that's going to result in a smooth, continuous function because those are easier to learn. So you want something where a small change to the input is going to result in a small change to the output, or the probability of winning. And I'll give you a counterexample to make that more clear. So if you have something like chess, where configurations of moves in spatial arrangements is really important, you're not going to get that smooth curve because this is Sea Cadet's mate. If any of you play chess, it's going to mate in 10 moves. And the important thing is, if you didn't have this exact arrangement, if you had just moved one of these pieces, like one of those knight pieces, it's not going to just slightly change your probability of winning. It's going to dramatically change it. So that curve for a game like that is going to be a lot more blocky and unpredictable and difficult to learn. So games like Othello, Go, chess, where relative positions of the pieces matter, are not going to be as good. Games where you're looking for canonical patterns are not going to be as good. So also the temporal difference neural network is going to break down in games that require a specific set of moves, like in chess, to reach checkmate. And these set of moves may be obvious to a human, but they're really bad for a temporal difference neural network. So you want to look for games that have a high degree of strategy and judgment, but less meticulation and calculation. And also, you want a game that terminates. So on backgammon, if you remember, the pieces were going around on a track, and you're rolling dice, and those dice are always going to be 1 through 6, and you've got 2 of them. So they're always going to be progressing the game towards the end of the game. You know, in a game like chess, you might end up in a situation where your pieces are doing a dance around each other in a stalemate. And what that could result in for your neural network is no reward signal at the end of the game ever coming out of it. So your neural network can't learn. So we actually had a situation like this for Race for the Galaxy. Technically, the end game states were the victory point pool being depleted or one of the players reaching 12 cards in their empire. But it's possible if the player, so it's a role choosing game and there's 5 to 7 different roles that you could be choosing. It's possible if the players chose the explore role where they're just drawing cards into their hand, neither of those victory or end game conditions would ever be met. And so we got around this by fudging the neural network and introducing an extra rule to it to say after 30 turns the game is going to end no matter what. And you can do that with your training, like when you're training a neural network. That doesn't necessarily have to get plugged into the final game, but taking little shortcuts like that can improve your neural network a lot. So although theoretically you could make a neural network like this that would be really good for a co-op game, and that would be an interesting challenge to make something that's going to help you a little bit but not too much. You wouldn't want to do it for a game like One Night Werewolf because you need multiple turns, obviously. Delayed rewards are the crux of a network like this because you're going to be back propagating those decaying rewards. Also, the acumen of your neural network AI is going to fall off as it approaches the end of the game, simply because it's got less of a wealth of forward turns to draw from. You can get around this by introducing some of that heuristic-driven AI to sort of counter for these endgame errors. And you're going to want your AI to be able to simulate the entire game. You need a fixed number of inputs, discrete legal moves, because if you have a fully simulatable game, you can generate limitless training data and make your AI infinitely better. And that's great because it's cheap and fast to do. So a game like Tag, which is really loosey-goosey, would not be a good candidate for this. And finally, a good candidate for a neural network like this is a game that has an existing player base. So board games are really good candidates because many of them already exist in physical form. They've got fan bases, and if you can digitize a board game, you can introduce something new but take advantage of that existing expertise in the player base. So, you know, there could be a fantastic board game that hasn't released yet. It might not be as good. I mean, you could still make a neural network. The problem is you're not going to get the advantage of testing it. So for us, when we released Race for the Galaxy, we put it on Board Game Geek. There's already tournaments. There's already a bunch of players who play up there. And it's great because we can test the neural network not just against benchmark AI, not just against, you know, this AI is a hard one. We're testing it on medium level to see how it does. You can test it also against benchmark human players. And that's going to be really good for identifying if there are issues. It's a lot slower than testing it against other AI, but If you do find bugs with this kind of network, they're most likely to be in your simulation. So anytime the simulation expects certain things to unfold and they don't, that's where we get the bulk majority of our bugs. We just have to do a tedious bit of bug hunting, but sometimes the player community can help point out some of our issues. So what's in the future for neural networks like this? I am not an AI researcher, but I can tell you a little bit about where we're going. And next thing that we're going to be doing is bringing Race for the Galaxy to VR, because we have a lot of experience in VR. And we can help try to resolve the crickets issue by pooling our mobile players, our PC players, and our VR players together so we can smartly fall back on a mobile or PC opponent if there is not a VR opponent available. We may migrate our neural network to the GPU side. We may not. We're pretty okay on CPU side, and the VR stuff taxes GPU quite a bit. It's interesting to hear that there's other teams here who are working on neural networks on the CPU side as well. Cover the black sheep. And we're going to be bringing that AI to life just like we did with Ascension. So with Ascension, you're inhabiting your avatars as you're playing the game, and we can bring some of those animations from players over to the AI to help communicate what's going with the AI. You know, long term in the future, you could use neural networks to generate voice or to generate, you know, detailed facial animations. We're not quite there yet on our team, but. And, you know, again, as a small company, we're focused on driving hard in a niche. So we're going to be doing Roll for the Galaxy next, which is a sister game to Race for the Galaxy. It's going to use a Keldon AI again. The challenge for this one, if you've played Roll for the Galaxy, is there's a lot more decisions that you're making on a turn. It's not just what role are you choosing, but it's, you know, you've rolled several dice and you're assigning all the different dice and you're determining what they're going to do. So that's going to have huge performance implications for us. So we'll have to figure that out, and maybe next year I can talk about what we did for that. So 20 years ago, it wasn't necessarily clear what the practical applications of temporal difference AI is going to be. But I think as board games get more and more popular, as we grow to be mainstream, this kind of AI is going to take off even more. It's worth figuring out. It's cheap. This picture is from Arby's, which is a chain restaurant, and they have a little meat bowl. So I guess board games are going mainstream. So anyway, I hope that you guys end up incorporating some AIs like this into your games, and I would love to hear what you end up doing with this kind of stuff too.